Hi everyone, I'm Cheryl. In this problem, we're going to be looking at the sequence 4 minus 1 over n and determining whether the sequence is monotonic and bounded. Well, before we begin, let's get a sense of what's happening with this particular sequence. I'm going to do that by looking at, let's just say, the first four terms. So a sub 1 will be 4 minus 1 over 1, which is 3. A sub 2 is 4 minus 1/2, which is 3.5. A sub 3 is 4 minus 1/3, which is 3.666 with the 6 repeating. And A sub 4 is going to be 4 minus 1/4, which is 3.75. All right. Why don't we plot these points on a Cartesian plane to kind of get a sense of what's happening? So when n is 1, I'm going to have an output value of 3. So that's right about here. And when n is 2, I'll be at 3.5, which is right about here. When n is 3, I'll be at 3.6 with the 6 repeating, which is right about here. And when n is 4, I'll be at 3.75, which is right about there. Okay, now these are only the first four terms in my sequence, but whether I look at it numerically or I look at it on the graph, I'm getting the feeling that this sequence is increasing. So I want to show that a sub n is increasing. Remember, if a sequence is monotonic, that means it's either strictly increasing or strictly decreasing. Now, just because I think it's increasing, or that's the sense that I'm getting, isn't a proof that it will always be increasing. So in order to show that my sequence is always increasing, I need to show that a sub n is always less than or equal to a sub n plus 1. In this particular problem, that means that 4 minus 1 over n will always be less than or equal to 4 minus 1 over n plus 1. Okay, so let's take a look at this. I'm going to start out with something I'm confident is true, and that is that n is less than or equal to n plus 1. Well, if that's the case, if I reciprocate each piece, I know that 1 over n will always be greater than or equal to 1 over n plus 1. And by negating both sides of my inequality, I know that inequality symbol flips, and so minus 1 over n will always be less than or equal to minus 1 over n plus 1. Then I'll add 4 to both sides, and I have 4 minus 1 over n is always less than or equal to 4 minus 1 over n plus 1, which is exactly what I wanted to show. Now, sometimes this algebraic way of showing that my sequence is increasing can be difficult. So as another option, you can think of your sequence as a continuous function. Think about connecting these dots with a nice continuous curve. If you were to do that, you could look at that sequence as the continuous function f of x equals 4 minus 1 over x. And then take a look at whether this function is increasing. Well, 4 minus 1 over x we can write as 4 minus x to the minus 1 power. And I know that I can determine whether a function is increasing or decreasing by looking at its derivative. So the derivative of this will be a positive 1 times x to the minus 2 power. Okay, we know that a function will switch from increasing to decreasing possibly when the derivative is 0 and when it's undefined. Well, this derivative you can write as 1 over x squared, and I notice that it will never equal 0 because of the 1 in the numerator. But it might be undefined when x is 0. So I can make a little sign chart, and I'll put my only critical number of 0 on it. And remember, because I'm only interested in values that are 1 and greater, I don't really care what happens on my sign chart prior to 0. But if I take any test point larger than 0, I notice that my derivative is positive, which means my function and, in turn, the sequence will be increasing. Okay, so now that I've determined that it's monotonic increasing, let's talk about being bounded. Well, I know that if I have a sequence that is strictly increasing, the lowest number will be the first term. So my lower bound is a sub 1, which I've already calculated to be a 3. The upper bound, we want to see what happens as n gets larger and larger and larger. So that means we're going to be taking a limit. So let's examine the limit as n approaches infinity of 4 minus 1 over n. As n approaches infinity, 1 over n goes to 0, and my entire expression goes to 4. So its upper bound is 4. Okay, now let's use a graphing utility to help confirm our results. There are actually several ways you could do this. The first of which is to think of my sequence as the continuous function 4 minus 1 over x, and simply graph it. So a nice window to use would be on the x-axis going from 1 to 10, and on the y-axis going from 0 to 5. And if you take a look at the graph of your function, you will see that you have a curve that has a lower bound of 3 and an upper bound of 4 and is strictly increasing. Again, remember, you're only looking at the particular data points, not really the entire function. Another possibility is to use a table. And in your table, you can set up your table so that it's starting at 1 and it moves in increments of 1. And then just have the y1 term be the values of 4 minus 1 over x. And you can see that the values are getting closer and closer to 4. It's a little bit like what we did at the beginning, but you're able to look at a lot more terms than just the first 4. You could also use lists and do a stat plot and get a picture of the individual data points. I hope that was helpful. Thanks.